Hello everyone. Today I'm going to talk about the how to prevent the correlated failures in service update. This is a joint work with a lot of people from different affiliations: Angchen, Ruzika, Piskach, Mehash, Balakrishnan, Bingchuan Tian, Bosong, and Haolian Zhang. So cloud services today relies on the redundancy techniques to ensure the reliability. For example, in Amazon AWS, they replicate the data across different servers. In Alibaba Cloud, we replicate the important service status across different regions. However, cloud outages still occurred very frequently in recent years despite the redundancy efforts. So these outage events are very expensive and made big losses. So you might be wondering, so why the redundancy efforts do not help in this case? So let me show one real example happened last year in Amazon AWS to illustrate the root cause. So in Amazon AWS, they have two layers, EC2 layer and EBS layer. And there are many physical machines in EC2 layer, and they rely on the storage support from the EBS clusters. So some application providers, such as Netflix, replicate the data across different virtual machines running on those physical machines. In this outage event, the power of one of the EBS clusters failed. And this problem leads to the cascading problems across different virtual machines in EC2 layer and undermining the redundancy efforts made by the application providers. So we say this problem is the correlated failures resulting from deep hidden dependencies. So this is our target problem today. The correlated failures are harmful and epidemic. They can propagate to all the redundant instances and undermine your fault tolerance efforts. So existing efforts have demonstrated that a lot of cloud scale outages today were caused by the correlated failures. And what is the state of the art? Whether they could help? So here's a typical service runtime. At the beginning, we initialize our service, right? And at some time, so the failures occur. So one type of existing efforts is the post-failure systems. So including diagnosis systems, troubleshooting systems, and provenance systems. So these systems aim to allocate localize the root cause of the failure in a reactive way. However, this type of approach cannot prevent the expensive service downtime. And at the same time, if you have a very complex cloud environment, it's very time-consuming to find out the root cause. So in order to solve the problem, the researchers also proposed the proactive auditing systems. So they try to use this type of system to detect the potential correlated failure risks ahead of time. And these systems are typically used in the service initialization. Let me briefly summarize how the proactive auditing systems work. Basically, they recommend the most independent alternative replication deployments before your service deployment. So first, the auditing system can automatically collect the dependency data from the target network, including hardware, software, and network. And then based on the collected data, the auditing systems can build a very important model named the fault graph to represent the dependency. Finally, the auditing systems try to find out the potential correlated failure risks by analyzing this fault graph. So the most important thing here is the fault graph. So let me briefly summarize what is the fault graph. So the root node of the fault graph is the redundancy configuration fail. And in fault graph, we have an AND gate. It uses the AND gate to connect all the redundant servers. The AND gate means if all the child nodes fail, the parent node fails. So this is exactly the meaning for the redundancy correlation. And then the fault graph uses OR gate to connect different types of dependencies. So OR gate means if at least one of the child nodes fail, the parent node will fail. And underlying each type of components, the fault graph uses the different gates to connect corresponding components. For example, the fault graph might use the AND gate to connect the redundant networking passes. And with the fault graph in hand, the auditing system can analyze it with some heuristic algorithms to find out the potential correlated failure risks. For example, in this example, might be the core one. So let's go back to the state-of-the-art discussion. So whether the state-of-the-art proactive auditing system is enough to prevent the correlated failure risks. The answer is no. So a lot of current correlated failure problems were actually caused by the updates in the service runtime. For example, last year in Microsoft, the DNS update caused a very big problem. And for another example, last year, so Google has a big problem because the operators updated a small part of the servers and caused the cloud scale outages. So straightforward solution might be to directly use the existing proactive auditing systems to analyze each updated service snapshot in the service runtime, whether it works. Unfortunately, the existing proactive auditing systems are super slow, but the updates in service is very frequent. So which means the slow auditing systems cannot match the frequent service update. In addition, there is another problem. So none of the existing proactive auditing systems can generate the improvement plans if we can detect any correlated failure risks. They only can tell you where is the root cause, but they cannot fix that. So this is our contribution. So in this work, we propose a system named the CloudCanary. So CloudCanary systems can quickly tell you where is the potential correlated failure risks that might be introduced by the update in service runtime. And auditing process is very quickly. And CloudCanary can also tell you how to generate the improvement plan if you can detect any correlated failures. So here's the workflow of the CloudCanary. And given updated service snapshot, we automatically collect the dependency data and generate the fault graph. This is the same as the previous efforts did. And one challenge here is how can we design the SnapAudit primitive to quickly audit the audit the snapshot. So the second challenge is how can we automatically generate the improvement plan? So before I talk about the details, I need to first describe one important terminology in fault graph. So this is the fault graph example. Important terminology in fault graph is the risk group. A risk group is a set of leaf nodes in fault graph whose simultaneous failures can lead to the failure of the root node. For example, the set including A2 is a risk group, and the set including A1 and A3 is another risk group in this example. But the set only including A1 or only including A3 is not a risk group. So risk group is very important because identifying correlated failure risks can be reduced to the problem of finding risk groups in a fault graph. So however, analyzing the risk group is an incomplete problem. That is the reason why the existing auditing systems are super slow. So now let me show you how we design the first primitive, named the SnapAudit. So the key insight of the SnapAudit design is the service updates typically only affect a small part of the service stack, which has been demonstrated by a lot of existing reports from the cloud providers. So this means the delta between different service snapshots in service runtime should be very slow. It should be very small. So based on this insight, we designed the SnapAudit primitive. So SnapAudit primitive first do something at the service initialization for the bootstrap, and then audit the delta of each following snapshot by incremental auditing algorithms rather than auditing the entire fault graph from scratch. So let me first show you how we designed FirstAudit Primitive. So given a fault graph example, so we want to assign the catch to each node in the fault graph. So each node has a catch, and each catch has a key. So the key is calculated by hashing the combination of the keys of the nodes, the node's child nodes. For example, if we want to calculate the key of the node F in this example. So we need to hash the combination of the hash values of the child nodes D and E. So the reason we do this is we can quickly find out which node is changed, because if any node is changed, the hash value will be changed. And we traverse the for graph from in a bottom-up way. And we fill the body of each cache by using the node's risk groups. So for example, for the node D, it has two risk groups, A and B. And for the node E, it has two risk groups, B and C. But how can we calculate the risk groups of F? So if we meet an AND gate, because F have an AND gate, right? So if we meet AND gate, we will calculate the Cartesian product of the child nodes risk groups. And in this case, we get 4 risk groups because we calculate the Cartesian product. And we simplify this set of risk groups by this way. So we get 2 risk groups. Similarly, we can calculate the risk groups of the nodes X and Y. And because we have an OR gate here for Z, and we could put all the risk groups of the child nodes together as the body of the cache of the node Z. And using the similar way, we could merge the risk groups of F and Z to get the risk groups of R. So by this type, we finish the first audit bootstrap. And now let me show you how we design the incremental auditing algorithm. So the insight of incremental auditing algorithm is we just want to audit the subgraph which has been affected by the update. So we want to find out the border nodes, and we analyze the border nodes to get the risk groups of the border nodes, and we merge the risk groups towards the root node. Let me show one example. So back to the running example, so we already have this type of cache, and suppose Z is updated, and a new subgraph rooted by Q has been added underlying Z. And because we use hash value for each node's key, so this update affects Z. And this value, the hash value has been changed. And of course, our hash value is also changed. In this case, we want to find out the border nodes. So because R and Z's hash values are changed, so the border nodes here are R and Z. And in the next step, we want to find out the risk groups of the node Q. Analyzing the risk groups is an NP-complete problem, so it's very, very difficult to solve in a quick way. So our insight here is to translate the for graph into the Boolean formula. If we have Boolean formula, we could leverage the set solver to quickly output a satisfying assignment. For example, if the set solver can output 101, that means we have a risk group including A1 and A3 in this example. So set solver is very fast and can get a very accurate result. However, standard set solver just output an arbitrary satisfying assignment. Our purpose is to get the top K critical risk groups. So we leverage a special type of set solver named the min cost set solver. Min cost set solver can output satisfying assignment with the least weight. And min cost set solver is very fast and can output the 100% accurate results. What we did is to set the values of leaf nodes in the given fault graph as 1. So let me show the example how we solve this problem. So this is the given fault graph, and we want to translate it into the Boolean formula, and we have assigned the value of the nodes as 1. So because the min cost set solver can output the satisfying assignment with the least weight, so this min cost set solver will output 010 case because this result has the least weight. But min cost set solver can only output just one result. What we want to have is the top K critical risk groups. How we did this? So we use a conjunction to connect the current formula and the negation of the resulting assignment to get a new formula, and we put this new formula into the mean cost size solver again. After k loop, we will have the top k critical risk groups. So now using the mean cost size solver, we can compute the risk groups of Q, and we get these risk groups. So in this case, we can update the Z risk group. Because this is OR gate underlying Z, and we just put the risk groups together to get the updated risk groups of Z. Using the similar way, we can update R risk groups. So in this case, we have finished our incremental auditing. So we only need to calculate the risk groups of the red parts, and we do not need to analyze the entire fall graph from scratch. So due to limited time, I just briefly describe how we solve the second challenge. So suppose we detect a risk group, including one element, the core router one, I saw in this example, and the operator so uses CloudCanary to write a specification describing how he wants to fix the risk. And the specification consists of multiple goals, including failure probability or some components. And our DepBooster component reads the specification and outputs alternative improvement plans. And at the heart of DepBooster is a synthesis algorithm, so which traverses a space tree and do the pruning according to the constraints specified in our specification. So the leaf nodes of this space tree are the alternative improvement plans. And please see our paper for more details. So far, I have talked about how we design the details of the CloudCanary, and this is the evaluation part. So let me briefly summarize the evaluation result. So we compare the CloudCanary with the state-of-the-art and evaluated CloudCanary using the real-world data set. So this is a comparison with the state-of-the-art proactive auditing systems, so including Indus, Recloud, and RapAudit. So none of the existing systems can generate the improvement plans, and only CloudCanary can simultaneously achieve the high accuracy and efficiency. So in the efficiency comparison, we compare the state-of-the-art the systems by randomly injecting some update errors. So due to the frequent updates, none of the state-of-the-art auditing systems can finish the auditing in real time. And we can see the CloudCanary not only quickly audit the problem and can automatically generate the improvement. So this is the key contribution of the CloudCanary. And we also evaluate the trade-off between the accuracy and efficiency. So suppose a random update affecting 20% components in a given service snapshot, and we can see the Indus. The Indus is very slow, but Indus can output the very, very accurate result. So because x-axis is the time and y-axis is accuracy. So this is the state of the art, and this is the result of CloudCanary. So CloudCanary is 200 times faster than the state of the art and offered 100% accurate result. We also evaluated CloudCanary using the real data set. So we observed the microservices, power sources, and the networking components, such as routers, switches, easily become the correlated failure risks. And CloudCanary can detect these real risks in a near 100% accuracy, and all the detected problems have been confirmed by the operator. So in conclusion, the CloudCanary is the first system for real-time auditing, and we address the two challenges here. One is SnapAudit, that can be used to quickly audit the updated snapshot, and the DepBooster can quickly generate the improvement plans if we detect any risk. And we also evaluated the CloudCanary with real trees and large-scale emulations. So this is the end of my talk, and thank you very much. I'm happy to take any questions.
Any question?
No. So, that's okay.
All right, I'm not sure if this fits within your context, but let me try it. So a lot of times the correlated failures are because of things that just weren't even in anyone's vision. So there was, I don't remember, I think it was in the 90s, there was this huge outage that took everybody out because it turned out that everyone had redundant network communications from AT&T and Level 3 and whoever, and they made sure nobody was reselling each other, and they were all independent, and they all ran in the same trench along the same railroad track, and when a train derailed there, it knocked them all out. So it wasn't in anybody's model. How do you deal with things like that where it's just sort of completely out of the scope because everyone thought they had 3 independent service providers that weren't reselling?
So, okay, this is a big question. So let me try to explain that. But if you have more things, we can talk about that offline. So first, so our target is just focused on one single cloud provider. And maybe, in this cloud provider, we have a lot of things. And actually, our work is mainly focused on, finding out the potential risks, but we rely on very important components that can automatically get the dependency data. So as what you just asked, so it totally depends on the granularity of the data collection. Mm-hmm. But if we could successfully get a lot of data collection, then in that case, we can successfully build a full graph and analyze it to get the result. Unfortunately, if we cannot get enough data source from the underneath, that might be hard. So, but back to your question, it's it totally depends on the granularity, of your cloud providers, what information you could provide, and that. But our focus on what we are focused on is the modeling and analysis. But anyway, yeah, I think that's a very very big question. We could discuss that offline, I think.
Yeah. Let's go ahead and take the last question, but as we do, let's switch speakers. So we'll.
Okay.
Remove your laptop, but go ahead and ask.
Mohammed from Facebook. Nice talk.
Yeah, thanks.
Did you consider inferring this dependency graph to build default model? Because sometimes you don't have domain knowledge to infer all of dependencies, the ands and ors.
You mean the dependency on what?
Like dependency between all of these components to.
Yeah, that's a great question. Sometimes that's very difficult because for the software level, right? So this paper is mainly focused on the hardware part, network part, but that's definitely the next step. We want to try to model the dependency between the components and microservices or something,
nice.
And try to solve that. But that's like what you mentioned, it's a very difficult thing. But great question.
Thanks.
Thanks.
All right, let's thank the speaker again.